space is just bookkeeping on the CPU. Like the GPU doesn't know anything about it. To tell the GPU about it, what we have to do is we actually have to program the memory management unit. And that handles the page tables and all those lookups and cache management of the page tables and all of that. So we essentially programmed the MMU to point to the various parts of the sysmem or frame buffer or whatever is needed. And in a modern GPU, everything, like pretty much all the state is in the frame buffer. So that means that all your textures, whether it's vertex, fragment, geometry, whatever, they're all in the frame buffer. All of your shaders, they're all in the frame buffer. All of the headers that actually describe your textures, saying that like, oh yeah, it's x wide by x tall and it's this format and it uses this sort of spatial locality scheme and stuff like that. That all goes in the frame buffer. And so we send a lot of commands, like once we've set up all that memory, we send commands down to host on a particular channel saying, all right, tell the 3D engine that texture 16 is here, texture 14 is here, and that we want to use this shader for the fragment stage and this shader for the geometry stage, and this is how the shaders are going to communicate, like how the output buffer from one ties to the output buffer for another, and how we're going to remap the data, and all sorts of things like that. We basically set up. And one thing too is textures. A lot of times somebody just says, hey, I want a texture that's going to be this by this and it's going to be this format. Done. Well, it's not that simple. Where does the texture reside? Does the texture reside here and we transfer it over the bus every time the GPU needs it? Does the texture reside here? And then we also have a problem that there's more than one app on the system and more than one app that wants to use the GPU. So how do we make them share? And so we have to manage context switching from our driver somewhat, so that all of these different applications can still, let's say I've got 512 megabytes in the GPU, and each application wants 300 of it, and we've got 10 applications. That's not going to work very well in a traditional system, but because we have the MMU, we have virtual addresses that these things can all address, and all we have to do is, when a new application comes in, we've got to make sure all the resources it needs are actually resident in here. But in order to make that work, we have to do paging from frame buffer to sysmem. So when somebody switches out, what we have to do is, if there's any data that we actually care about from this application that we need when it wakes back up, we have to page everything off to sysmem. And then after everything's paged off, we need to reprogram the MMU so that the next guy coming on can actually have his stuff. And then, if his stuff was resident before and is expected to have valid data, we've got to page it back in. What's worse, there's a fixed number of hardware channels. So these channels, there's 128 of them. And some of them are tied up in system usage, so in practice there's like 110 of them. Now, each one of these channels is a context, basically. If you have a lot of contexts going, which is not uncommon on an Apple operating system, Apple might have 300, 400 contexts going on. Obviously, we don't have 300 or 400 channels. So that means that we have to do special under the hood stuff to make sure that we can kind of do virtual channels and have things share the same channel, which means that we've got to do all sorts of state juggling. And all this is something that the app does not care about and doesn't want to care about. And so we have a lot of logic in the driver to figure out how to handle memory, how to make sure that it's suballocated. And so, like, we have suballocators that basically reserve chunks of memory, so that every time we operate on the MMU, it's really expensive. And so if we can avoid operating with the MMU and just suballocate so that different applications actually kind of share the same chunk of GPU allocated memory, we can run a lot faster. And I don't even want to guess how many thousands of lines of code the driver is, millions, it's a lot. And I would say 80% of what I do, at least when it comes to performance, is memory, optimizing memory usage. There's one application in particular that was terrible with memory usage. It was a video processing application, and it was, it's a really widely used video processing application. The guys who wrote it are smart. I mean, they're really smart. They know exactly how to write this software, but they don't really know how graphic stuff works. And so what they would do is for every frame, they would have really complex compositing effects and stuff like that, but every frame they would allocate all new textures and do all the work for that frame, and then destroy the textures at the end of the frame. and they were just having horrible performance. I mean, it was really bad. And somehow or another, AMD wasn't having the same cost for dealing with memory management, and so it ran faster on AMD than NVIDIA. I was like, oh my god, the sky is falling, you know, and we had to find out a way behind the apt back to make it faster. And so there's things like caching the textures. So if they create 20 textures in every frame and destroy 20 textures in every frame, we say, well, maybe they don't really mean they want to destroy the texture. And then next time they come in to create textures, we say, maybe this is one of those that they were using before and they really want to reuse it. And so we'll check for that and just reuse. And we try and reuse a lot of things. You know, one of the mantras is, as a programmer, the more you can reuse stuff on the GPU and keep things on the GPU, the happier you'll be performance-wise. But not everybody knows that. And even if you know that, it's hard to keep that in the forefront of your mind. A lot of what the driver tries to do is tries to figure out if there's a way we can optimize for you. So,
thanks.
Yeah.
You mentioned that you use the unified 40-bit addressing.
Yeah.
And then you just said, you know, when you were talking about this, is that when you run out of VRAM, you'll swap stuff out to system memory. Since you have up to a terabyte worth of address space with that 40-bit, do you eventually, on the driver on the CPU side, swap stuff out to disk if necessary, if there's not a terabyte worth of system memory, or?
Oh, well, so we don't explicitly swap out to disk. We always swap out to sysmem, but the sysmem can be swapped out to disk.
Right, okay.
And that 1 terabyte of memory is really 1 terabyte of virtual address space, which means that every context essentially gets 1 terabyte of virtual address space. Obviously, you know, you've got 40 contexts, that's 40 terabytes. If every context were to use every bit of that, you would need one beefy system. But it's really handy for avoiding certain kinds of fragmentation, to have a virtual memory system, there's all sorts of reasons where it's really nice to have that 1 terabyte of space. And also, one thing I should mention is because each application has its separate address space in the GPU, so to speak, you can actually get memory protection that way. Because you can't really stomp on anybody else's memory. Because the MMU basically won't let you.
Do you do any kind of optimizations? Because you mentioned there are certain applications where it's nice to have that much space to avoid fragmentation. Do you do any kind of optimizations to see, like, well, it's really it uses more VRAM than we have, but overall the individual fragments don't, so we can collapse them down?
Yeah, I talked a little bit about our suballocator. And our suballocator basically tries to get things as close together. It tries to keep data from the same application, or the same context, together as much as possible, so that you get good locality. And then we also have a concept of certain high priority resources that need to be fast no matter what. And we try and make sure that those stay in the frame buffer no matter what. And for things that you just run out of room, you don't want to thrash with paging things on and off all the time. So sometimes it actually makes sense for us to say, okay, fine, we're going to leave you in system memory and just access you that way. Even though it's painful to go across the bus, we're only going across once. Whereas if we're paging, we'd be going across all the time. And actually, that's one thing that we see in World of Warcraft, actually, is we have to be careful about paging in World of Warcraft, because the way they use memory, they actually use a lot of memory. And we've done a lot of stuff to make sure that we don't let them fall off a cliff, essentially, with memory access. So. Anything else?
Yeah. One more thing. It sounds like since you guys do a lot of stuff in terms of managing all of the state that's on the GPU, is there a sort of concordant thing of moving more of that onto the GPU and having more general purpose flexibility that way for it to manage itself?
Yeah, there definitely is. I probably can't speak too much in particular about that, but yes.